susceptibility. We're going to review quantum numbers, electron configuration. We're going to see how we ionize atoms. We're going to talk about d orbitals and how the d orbitals may cause an unexpected splitting in the energy levels. We're going to talk a little bit about magnetism. We're going to go over the equations and calculations you need to understand to determine the number of unpaired electrons. And we're going to talk about ligands and how the strength of certain ligands can impact the splitting of these energy levels. All right, so a quick review of Schrodinger equation. So we have H psi equals E psi. So H is a Hamiltonian. It's the sum of the kinetic and potential energy of our system, whether it be one electron or many electrons, okay? And that gives us an eigenvalue energy and the wave function again. Now, the magnitude square of the wave function is our probability density, okay? Basically our orbital, okay? And the orbital is a probability distribution map showing where the electron is likely to be found. Okay, so there are four quantum numbers, n, l, m sub l, and m sub s. And these come out of the exact solutions for the hydrogenic Schrodinger equation. Okay, that's H psi equals E psi for the hydrogenic atom. Okay. We're going over this quickly so that we know how to fill our electron configurations. Okay, so our principal quantum number goes 1, 2, 3, 4, so forth and so on. Our angular momentum quantum number goes 0, so n equals 1 can only have L equals 0. N equals 2 could have L equals 0 or 1. So the first principal quantum shell can have only S subshells. The second principal shell can have S subshells and P subshells. The third principal shells can have S, P, D, so forth and so on. An orbital, no matter what type of orbital there is, an orbital can only hold 2 electrons. Only 2 electrons per orbital, okay? Now, so let's look at the P subshell. In a P subshell, there are 3 P orbitals, okay? And that P subshell holding those 3 P orbitals can hold 6 electrons. But keep in mind that a given orbital can only hold 2 electrons. It's that there are 3 P orbitals in a P subshell. There is one P orbital, there is one S orbital in an S subshell. There are 5 D orbitals in a D subshell, okay? And thus a D subshell, which has 5 D orbitals, each holding 2 electrons, the D subshell can hold 10 electrons, okay? And then the principal shell capacity 2, 8, 18, 32, so forth and so on. Okay. So how do we fill our orbitals? Well, hydrogen, we know we start with the first principal shell, n equals 1, okay? And we fill 1 electron in the S subshell, okay? Now, we're going to continue this for other atoms. You've done this many times for many atoms, but except for the hydrogenic, except for the hydrogen, all these others are just approximations. Okay, okay. This is just how to represent it with a diagram. Again, for the H, we just have a one electron in a 1s subshell, and we would write it spin up. For helium, we would have 2 electrons in a 1s subshell, and it would be spin up, spin down. And so the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So no 2 electrons can have the same address, okay? So let me go back to really quickly, let me go back to my, so no electron can have all of these 4 principal numbers the same. We can have this the same, this the same, this the same, but then this one's going to be either spin up or spin down, okay? Okay. Makes sense. Okay. Now, so this is some language that's maybe used improperly in some textbook. So orbitals with the same energy are said to be degenerate, but orbitals don't have energy. It's the electrons in orbitals that have energy, okay? If, for example, I can have an empty p orbital floating somewhere over here. It doesn't have energy. If there's an electron in that p orbital, then the electron has energy. Like, for example, consider Earth going around the sun. There is a path that defines how Earth will move around the sun. That path is just some location in space. That location in space doesn't have energy. It's the gravitational energy between Earth and sun that has that energy. The electrons have the energy in the orbitals, not the orbitals themselves. The orbitals themselves are just regions of space. Okay, great. Now, let's consider again just a hydrogen atom. Okay, so all subshells in each principal shell in the hydrogen atom have the same energy. However, for multi-electron systems, there's going to be a splitting of the subshell's energy within a same principal shell. We'll see that next. See how? Let's look at the fourth principal shell. See how there's a splitting in the energies? Well, for the hydrogenic atom, these would all be the same. But for multi-electron atoms, these are different. The splitting is caused by the different orbitals penetrating into other orbitals. It is also caused by screening of inner electrons from screening of outer electrons by inner electrons. Okay. Now, let's say we have some multi-electron system, and we need to fill our electron configuration. How do we do this? Well, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, so forth and so on. We know that these are subshells, okay? We know that the s subshell has one s orbital, so 2 electrons can go in an s subshell. This is another s subshell. 2 electrons can go into an s subshell because it has one s orbital. Now, a p subshell has 3 p orbitals. So each of those orbitals can have 2 electrons. So we can have 6 electrons in a p subshell. 2 electrons, 6 electrons, 2 electrons, 10 electrons, so forth and so on. Okay? All right. So don't look at your periodic table. Don't look at your chemistry book. Just try from memory to write out the electron configuration for chromium. We know chromium has 24 electrons. So, try to write this out. 1s2, so forth and so on. You can pause the YouTube video and try to write it out. Okay. So now, is there anything interesting about chromium? Maybe we forgot something. So chromium is one of those exceptions. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But it's not 4s2, 3d4. With chromium, remember that it is more energetically favorable to fill the 4D, to completely fill the 3D subshell. So we promote one of the electrons from the 4s subshell into the 3D subshell. This is actually more energetically favorable than 4s2, 3d4. Okay. Now let's review paramagnetism and diamagnetism. So paramagnetism results when the atom has unpaired electron. In this case, there's going to be an attraction, a relatively strong attraction to an external magnetic field. In contrast to this, atoms with all their electrons paired experience diamagnetism. That is a weak repulsion to an external magnetic field. Okay, we know one of our noble gases, argon, has all of its electrons paired. We see all the electrons paired here. So argon would be an example of a diamagnetic material. If we would put argon in a magnetic field, we would experience a weak repulsion to that magnetic field. Okay, so how do we ionize atoms? So if we write out the electron configuration for zinc, it would be something like this. So atomic zinc would be diamagnetic. But let's ionize zinc once. So where do we remove that electron? We don't remove it from the 3D subshell. We remove it from the outermost subshell. We remove it from the 4s subshell. So zinc plus would be 4s1 3d10, paramagnetic, since it has one unpaired electron. Okay, so here's a problem for you. So we have this complex. We have iron with these 6 water molecules, and we say this complex has a 3+ charge in it. Now, would this be paramagnetic or diamagnetic? Okay, keeping in mind that neutral iron has 26 electrons. Okay, so you can pause it and work on it for a little while. Okay, so first we write out neutral iron with 26 electrons. Then we remember that water is neutral. Okay, since water is a neutral ligand, the iron is going to be iron 3+. So we have to ionize iron 3 times. We take away the 4s electrons first, okay, and then we take away one of the 3d electrons, okay. So we're left with a 3d5 compound. Since we have a 3d5 compound, there are 5 unpaired electrons. So this complex would be paramagnetic, okay? Now, what we'll see near the end is more comments on these ligands here. So I say water is a neutral ligand, but we say water is a weak field ligand, or at least not a strong field ligand. So water is not going to split our d orbitals. Okay, I just threw that in there a little bit. So just keep that in the back of your mind, and we'll see some consequences of this later with some strong field ligands. All right, so now d orbitals. I just want to remind you what d orbitals look like. They look something like this. So now we have these 3 d orbitals, dyz, dxz, dxy. Now they're on the given plane. So the dyz orbital is on the yz plane, and these two are on their corresponding planes. And this one is on this plane, and this one is along this z-axis. Okay? Great. Now, let's take a look at these two orbitals in particular. See how the lobes are along the axis here? Okay? So now let's say I have let's say I have an octahedral complex. So I have 6 water molecules, one here, 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 and here. Okay. So now the orbitals from these water molecules are going to um, come in close proximity to these orbitals along these axes here, 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 here. Okay? Now, the electron repulsion from these orbitals will, to some extent, split the field, it's called. So we're going to split these, we're going to move these two d orbitals to a slightly higher energy state than these low-lying orbitals. Now, there are some consequences of this. With water let's try to predict some consequences. So, with water molecules, this splitting is not so great, okay? But what would happen if we have some ligand that has this large energy splitting, or causes this large energy splitting? Well, then these two orbitals would be the energy of these orbitals, if they were filled by electrons, or electrons, would be much higher than these down here if these were filled with electrons. So now we generally fill d orbitals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But why do we do that? Why do we fill orbitals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Well, we do that because we don't want the electrons to pair up, at least not at first. When we pair up electrons, there's some penalty. The electron density of the electrons repel each other. So there's an energy penalty. So we fill 1, 2, 3, 4, 5. But there may be instances where this is so large that it's actually more energetically favorable to fill 1, 2, 3, 4, 5, 6 before going to these higher energy orbitals. If they had electrons in them. They don't have energy right now since there's no electrons in them. I think you get that point. Okay, so we'll come back to that. I'm actually going to repeat that. All right, so let's just quickly talk about some magnetic properties. So if an electron can produce 2 types of magnetic fields, one basically due to its orbit around some nucleus, and one due to its intrinsic spin. Okay. Now, let's say I have some material and I place it into a magnetic field. Let's say it's a B field. Okay. The strength of that field within the material, let's call it H. Okay. Now, the material's response to that B field, let's call it M. Okay. Now, the ratio of these two quantities, M divided by H, is the susceptibility of that material, chi. Okay. How this material is impacted by this magnetic field. Okay. Now, susceptibility is dimensionless. Okay. But if we divide the susceptibility by density, well, we obtain the mass susceptibility, chi g, with units of centimeters cubed per gram, inverse density. Okay. So why is that useful? Okay. So here again is that chi g. Okay. Centimeters cubed per gram. I hope I'm going back to my last slide. I hope I said centimeter cubed per gram. Forgive me if I said something else. So mass susceptibility has units of centimeter cubed per gram. All right. So we have this susceptibility of centimeters cubed per gram. And we're going to calculate it based on this equation here. Now, this isn't like a fundamental equation of nature. This is just some parameterization based on the experiment. Okay, I'm going to just tell you what these are, and then I'm going to go to the experiment. So we have the length of the sample, the calibration constant of the balance. The calibration constant of the balance is like an offset because the balance isn't perfect. Okay, so it calibrates off of many samples to try to get the right whatever value it's looking for, maybe number of unpaired electrons. This R is the response, the machine response. Okay, this is the machine response for an empty tube. Okay, this is the mass of the sample. Okay, and in grams, and this 10 to the 9 is to account for units. Okay, so let's just take a quick look at the units we have here. So length, okay, we have in centimeters. Okay, and mass we have in grams. Okay, great. So and this is in centimeters cubed per gram. So that means this R, the calibration constant, is dimensionless. So this R has to be centimeters square. So basically, you can interpret this R in a few ways, but basically, it's kind of an effective area of magnetic field lines. Okay, so now let's leave the lecture and go to the experiment real quick. So here is your virtual experiment. So what are you going to do? Well, in the lab, you have here's a picture of the actual samples in the lab. You're not doing this semester, but you're welcome to come back next year to do it if you want. So basically, we have these samples here. This is a virtual lab I wrote. So we have these samples here, and what we do is we would take each of these samples, we would tear this, get this to about 0. We would take each of these samples, put them in the magnetic susceptibility balance, and record the response, okay? Let's just try this first one. Okay, so we put it in there, and we get a response of 1,254. Great. Let's go randomly to this one. Oh, this one gave me a negative value, negative 19. So if we have a large positive number, so that would yield a paramagnetic. That would tell us that it's a paramagnetic material. If we have a small negative value, then that's going to tell us that it's a diamagnetic material. All the electrons are paired. Now let's scroll down. I made a simple diagram. That's a coil of wire. Forgive me, I had trouble drawing a coil of wire. Okay. This is the internal workings of the magnetic susceptibility balance. So I took my potassium dichromate and pretended to put it into my instrument. So what happens? So potassium dichromate is diamagnetic. Okay, so we get a weak repulsion, small negative number. Okay, so it's going to be weakly repelled by these magnets. Okay, so what does that mean? Okay, so the net force is going to see how there's the net force. Well, this force, these forces are going to cancel. But what about these forces? So these forces here are going to push down on this magnet. Okay, so there's a bar here. Then there's a fulcrum. Since this is going down for diamagnetic materials, this is going to go very slightly up. Okay, so then there's a current that's going through this coil of wire. So this this pair of magnets is going to move slightly up, slightly adjusting the reading here. Okay, so then it's calibrated to give you a negative number for diamagnetic materials. If, for example, we put something like this mercury sample in, we would get, let's say instead of this potassium dichromate, we would have this mercury sample. It's paramagnetic, okay? So that would have a strong attraction. So the vector forces here would pull this magnet up slightly. Since this is going up, this is going up a fair amount. This is going down a fair amount. This would go down a fair amount. So that is calibrated to give a larger positive value. A good time to say this. This is you're going to have to know this. So this is Hg2CO2. Okay, you'll need that. to figure out the number of unpaired electrons on the CO. There's no unpaired electrons on the mercury in this sample. All the unpaired electrons are going to be on the cobalt. Okay, so again, the virtual experiment, the virtual experiment is fairly easy. You just have these 12 samples. You just click on them one by one and write down the response. I did this in the lab, and I just made the web app produce the same responses as you would see in the lab. And potassium permanganate is diamagnetic, so you should get a small negative number for potassium permanganate. The most interesting one, where is it? There it is this one here. So when you calculate the number of unpaired electrons on this iron, your first thought is that you first think that you'll have 5 unpaired electrons because you'll have a D6. So you work it out. So this iron is a D6 iron, and of course you go 1, 2, 3, 4, 5, and then you have one more electron. You fill it. You would think you would fill it in the the first d orbital. So it looks like you have 4 unpaired electrons, but we have a diamagnetic. So something odd happens here. So there's actually this. I'm going to get to this in just in a minute. This Cn minus is what's called a strong field ligand. What it's going to do is going to push up those 2 higher energetic d orbitals, and the splitting will be very large. Okay, so keep that in mind, and we'll get to that on the slides in just a few minutes. Going back to the lecture. Okay, so we're back here. Okay, so we understand. No, we don't. I forgot to say something. So I can say it here. The length is the length of the sample in centimeters. I give this to you in the lab manual, and the mass is the mass in grams. I give that for you in the lab manual. C balance for all of them is 1.19. The R is what you find, and the R0 is the response to an empty tube. I think it's -2. I think I see that on the next slide. It is, yes, great, I remembered right. Okay, so it's -2. Okay. This here is the mass of the empty tube. This here is the mass of the empty tube plus the mass of the sample. So you have to subtract the difference of these to get the mass of the sample. This is the length of the sample in the tube. This is the R. This is what you have to get. And this is R0, okay? Right here is the Curie temperatures. And so you calculate this, and this. So what are these? Okay, so I'm going to go back a slide. So we know how to calculate this chi-g. I give you this. I give you this. You find this from the lab. I give you this, and you find this in the table. So you calculate the chi-g's for all of these samples. Okay. Then you take this chi-g. You multiply it by the molecular weight of the sample, including the water molecules. Don't leave out the water molecules. You divide by Z, where Z is the number of magnetic ions per formula unit. For example, in this case, Mn2O3, Z is 2 because we have 2 magnetic ions. Okay? Then you calculate U effective. I'm going to go back. So this is U effective. Okay? It's fairly easy to calculate. Okay? But don't give me imaginary numbers here. This equation is only applies if there are unpaired electrons. So if you have a diamagnetic sample, just say U effective is 0. Okay. Then the square root of 1 plus U effective squared minus 1 is the approximate or estimated number of free electrons in the on the complex. Since we divide by Z, number of magnetic ions per formula unit, it's number of unpaired electrons on the atom. Okay. Okay. I want to say one more thing. So we calculate U effective. We calculate square root of 1 plus U effective squared minus 1. We get this number of unpaired electrons. Okay. So then what we do is we calculate by oxidation states. We calculate dm. This is like, for example, iron 3 plus will be d6. Okay. Then we calculate number of unpaired electrons based on this this here. So if it's, let's say it's a d6 if you have a d6 with octahedral complex with weak field ligands, then you would fill 1, 2, 3, 4, 5, and then the 6th electron would go in the first d orbital, so you would have 4 unpaired electrons. Okay, but let's say we have Cn minus, a strong field ligand. Okay, so strong field ligands create a large splitting in the field. Okay, I'm going to go back several slides. Here, if I talked about water being a weak field ligand, or at least not very strong. But if I have Cn minus, that would be a strong field ligand. So that would create a large gap here. So if we had if we had a Cn minus or some other strong field ligand with a large gap, and maybe we had D6 like an iron complex that's iron D6, then we would go 1, 2, 3, 4, 5, 6, and all the electrons would be paired. So in that interesting iron sample I showed you on the experiment, let's take a quick look. Here's the interesting iron sample. See how we have, see how this D6 iron, we would think, well, D6 iron, probably 4 unpaired electrons, but wait, we have it appears to be diamagnetic. Since it's diamagnetic, we know all the electrons are paired. But we think a little more, and we realize, oh wait, it's Cn minus, so we have a strong field ligand, so that'll make a large energy gap. So we fill the low-lying, the 6 electrons go in the 3 low-lying d orbitals, and it does end up being diamagnetic. Okay. All right. And so, for this course, basically assume if you have Cn minus, it's strong field, and then everything else is just assume it's relatively weak. I just said that. Okay. Okay. So just in terms of a diagram for you, again, summarizing, if we have something like a D6. This would actually be a D5 complex. So if we have a D5 complex with a weak field ligand, let's say water molecules, then we would fill 1, 2, 3, 4, 5. But if we have a D5 complex with a strong field ligand, like Cn minus, then we would fill 1, 2, 3, 4, 5. Okay, but again, the other example, the other iron was D6. This example here is D5. Okay, so here is a problem for you. So, well, this semester I don't give you exams. I just give you review assignments. But on your review assignment, you'll definitely see something like this. So let's say you have this cobalt sample, and it has these Cn minus ligands. Well, we know that Cn minus are strong field ligands, so why don't you write out the entire electron configuration for cobalt, okay? We know Cn minus, so we have 6 of those, and we know this is going to be 3 minus, so we know that cobalt has to be 3 plus. So write out the electron configuration for cobalt 3 plus. Then consider the ligand and determine whether this will be paramagnetic or diamagnetic, and then describe the sign and magnitude of the response you find. Okay, so think about it for a little bit, pause YouTube, and just kind of think about this problem. This problem really kind of summarizes everything. All right. Okay, so as I said, we have cobalt 3 plus, okay? So we take away the 4s, the two 4s electrons, okay? And then one of the 3d electrons, and we're left with a D6 compound, okay? But since we have a D6 compound with Cn minus, a strong field ligand, okay, the electrons are going to fill 1, 2, 3, 4, 5, 6, and all pair up, okay? So this will be a diamagnetic compound. If we put this in our magnetic susceptibility balance, this will yield a small and negative response. Okay, so just some notes when you're working this out. So this one, just keep in mind, I said earlier, this is Hg2CO2, okay? You can work out that there won't be any unpaired electrons on Hg2 plus. So there will be on cobalt 2 plus, of course. So the number of magnetic ions per formula unit for this compound is just Z equals 1, okay? Just keep that in mind when you're doing your calculations. So this lab is, I really wish you could do this in person. You can come back and do it in person. The numbers and the number of unpaired electrons, it all works out perfectly. So this one, Mn2O3, I think, so there's 2 magnetic ions per formula unit. Okay, so you would write out the electron configuration for Mn. We know it has 25 electrons, and we know that O is 2 minus, so that means Mn has to be 3 plus. Okay, so we know Mn 3 plus is D4, and we write 1, 2, 3, 4, and we know it has 4 unpaired electrons. Okay, so if we had Mn2O3 and we put Mn2O3 into our experiment, we would get a large positive response. Okay, let's just, so that you believe me. Well, I think I have Mn2O3. There it is. So Mn2O3, we have a large positive response, very large, because there's 4 unpaired electrons per atom. Okay. Again, next year, we're remote this year, but if you want, and for this experiment or any of the other experiments, if you want to come back next year and do them, you're welcome to come back. And if you're not from Rutgers and you want to use my my virtual lab, you're welcome to. I'll post a link with a YouTube video. Okay, well, thank you.